Imagine an array that receives many range updates. Add 3 from index 1 through 4, then add 2 from index 3 through 6, and keep going. The direct method touches every cell inside every range. With many updates and long ranges, the same cells are rewritten again and again. A difference array changes the viewpoint. Instead of editing the whole range immediately, we mark where the change starts and where it stops. After all boundary markers are placed, one left-to-right prefix sweep rebuilds the final array. That is the core idea for the rest of this tutorial. Before the shortcut, look at the input array and the 2 range updates we need to apply. The brute force plan is simple. For each update, visit every index in that range and change the value in the array. Now apply add 2 on indices 3 through 6. Notice indices 3 and 4 are touched again, even though we just updated them. For only 2 updates this is fine, but the work is proportional to the total length of all ranges. With many long ranges, brute force can become q times n. A difference array stores changes between neighboring positions. Instead of asking what is the value here, it asks how much did the value change from the previous cell. Look at a range update that adds 3 from index 1 through 4. The actual values may be different, but the extra amount added across that interval is the same plus 3. There are only 2 important moments. At index 1 the value jumps up by 3, and after index 4, at index 5, the value drops back down by 3. So the range update becomes 2 boundary markers, diff1 plus equals 3, and diff5 minus equals 3. A prefix sweep later turns those markers back into the full array. Now walk through one update completely, add 3 on indices 1 through 4. This update becomes just 2 markers in the difference array. At the left boundary, index 1, place plus 3. This says, from here onward, the running value should increase by 3. Just after the range ends, at index 5, place minus 3. This says, from here onward, turn that added 3 back off. The running sum is just the prefix sum of the difference array. Now we will sweep one index at a time. Index 0 has diff 0, so the running sum stays 0. The result is input 2 plus 0, which is 2. Index 1 has plus 3. Add that to the running sum, so running becomes 3. The result is input 1 plus 3, which is 4. Index 2 has diff 0, so running stays 3. The result is input 4 plus 3, which is 7. Index 3 also has diff 0, so running is still 3. The result is input 0 plus 3, which is 3. Index 4 has diff 0, so the plus 3 is still active. The result is input 3 plus 3, which is 6. Index 5 has minus 3. Add it to the running sum, and running returns to 0. The result is input 2 plus 0, which is 2. Index 6 has diff 0, so running stays 0. The result is input 1 plus 0, which is 1. Index 7 has diff 0, so running stays 0. The result is input 5 plus 0, which is 5. The result is exactly what the range update meant, unchanged values outside the range, and 3 added to indices 1 through 4. This prefix row is only for learning. In code, we do not need to store it as an array. We keep one running variable, update it from diff, and use it immediately for the current result cell. Now apply 2 updates together, add 3 on indices 1 through 4, and add 2 on indices 3 through 6. For the first update, place plus 3 at index 1, and minus 3 at index 5. For the second update, place plus 2 at index 3, and minus 2 at index 7. The markers all live in the same diff array. Now take the prefix sum of diff. Where the 2 ranges overlap, the running sum becomes 5, because 3 and 2 are both active. Finally, add that prefix value to the input array. The overlapping cells receive both updates automatically. One small edge case happens when a range reaches the last index. Here we add 4 on indices 5 through 7. The start marker is normal, diff 5 plus equals 4. The stop marker should go at our plus 1, which is index 8. But if diff has only n cells, its last valid index is 7. There is no slot for index 8. So we make diff length n plus 1. The extra cell stores the stop marker, and the final result still uses only indices 0 through 7. Difference arrays are a great fit when updates come in batches. You apply many range updates first, then build the final array once. They are especially useful when every update has the same shape. Add a value to every index from L through R. They are not the right tool when you need the current answer after every update. Then doing a full sweep each time would be too slow. So the short rule is, use a difference array for offline range updates and one final reconstruction. For brute force, each of Q updates may touch up to n cells, so time is O, Q times n. With a difference array, each update changes 2 markers, and the final sweep is linear, so time is O, Q plus n. The extra space is O, n, for the difference array. Define a routine that receives the input array and all range updates. Store the length of the input array. Create a difference array with one extra cell for the R plus 1 marker. Loop through every range update. At the left boundary, add X to start the update. Right after the range, subtract X to stop the update. Start the running prefix sum at 0. Prepare the result array. Sweep over the original n input positions. Add the current diff value into the running sum. The final value is the input value plus the running sum. Return the finished result array.